Just reminding ourselves how interference works. This one's nothing to do with optics, but just like a warm-up question. Let's say the speaker's at the front of the classroom. Let's say we've got a speaker here, and we've got a speaker there. They're 3 meters apart. When you observe a spot 4 meters in front of one of the speakers, so what I meant by that is like a point way over here. This distance is 4 meters. When you stand at that point, you hear the sound as loud. Loud means constructive interference. Interference is all about phase. Sound isn't a transverse wave, but if we wanted to imagine it was, if it's a loud spot, that means whatever wave is coming from speaker number 1, when it gets to this point, let's say it gets there as a crest, that means the speaker coming, or the sound coming from speaker number 2 is also getting there as a crest. A split second later, it flips to a trough and a trough, then crest and crest, then trough and trough. That's what it means to be loud. It means it's constructive interference. It means that the waves are in phase with each other. If those waves are in phase with each other, really what it comes down to is how much farther, the way I've drawn it, the wave from speaker 2 travels farther. How much farther does this wave go compared to how far the wave from speaker 1 went? A little bit of Pythagorean theorem. The whole distance, let's call it x, the whole distance from speaker 2 to that point we're curious about, it's a 3, 4, 5 triangle. So the whole distance from the speaker 2 to that point is 5 meters. That means that the extra distance is 1 meter. Interference is all about how much farther, when there's two sources, how much farther one goes than the other. And constructive interference is always on a multiple of lambda. So what that means is that 1 meter of extra distance, it would have to be a full lambda for that to happen. Or the 1 meter, maybe it's 2 full lambda. Or the 1 meter, maybe it's 3 full lambda. For any of those cases, if the lambda is 1 full meter, that's going to put those two waves in phase. If lambda was half a meter, that's going to put them back in phase. If lambda was a third of a meter, that's going to put them in phase when they get to that point. That's what it means to be constructive interference. The extra distance that the wave that traveled farther must have traveled farther by a full multiple of lambda. The question doesn't ask it, but just for kind of completeness, if the question brought up destructive interference, then that extra meter would have to be half a wavelength. Or maybe it's 1.5 wavelengths. Or 2.5 wavelengths. If the extra distance is off by a half, that would put them out of phase. That would make it a quiet spot. So the key here that we'll pull forward when we're doing optics is to remind you that interference, when there's two waves interfering, if one wave travels farther than the other, whether it's constructive or destructive interference depends on how much farther. When we do this subtraction or find that extra distance, if the extra distance is a multiple of lambda, that puts them in phase in constructive interference. If the extra distance is off by a half, that puts